Welcome to the channel. I'm Carlos Ortega, and I'm excited to explore the amazing worlds of physics and chemistry with you.
From the moment we wake up, we're constantly pushing and pulling. We stretch a rubber band, push a shopping cart, or drag a heavy backpack. We apply physical effort so continuously that we hardly even register it. Because of this constant effort, we develop a very specific intuition about how motion works. When we stop pushing that shopping cart, it slows down and stops. When we let go of a thrown ball, it eventually hits the ground and rolls to a halt. Our everyday experience tells us that rest is the default state of objects. But objects on Earth don't just stop on their own. They slow down because an invisible, persistent force is actively rubbing against them: friction. The floor grips the wheels of the cart, and the air pushes back against the ball. Take away that terrestrial resistance, and the entire picture changes. Stopping isn't the natural default of the universe at all. It's just a local effect of living on a planet covered in atmosphere and textured surfaces. To understand how motion actually works, we have to look to Isaac Newton and his first law of motion, commonly known as the law of inertia. Inertia tells us that objects resist changing what they are already doing. If you throw a ball in the frictionless vacuum of space, there is no air or surface to rub against it. Without friction to slow it down, that ball will travel in a straight line at the exact same speed forever. As we can see in these technical panels, a cactus sitting quietly in the desert and the Voyager probe speeding through the solar system at a constant velocity share the exact same physical status: equilibrium. Equilibrium simply means that all the invisible pushes and pulls acting on an object perfectly cancel each other out. If the force pushing left equals the force pushing right, the mathematical total is zero. As long as that net total remains zero, a stationary object stays put, and a moving object keeps cruising. To truly alter an object's speed or direction, that perfect mathematical tie has to be broken. So, what exactly happens when those forces do not cancel out? To answer that, we have to measure force as a mathematical vector. It is an arrow that tells us three specific things: its magnitude, or intensity, its direction on a line, and its sense, meaning which way the arrowhead points. Newton's second law establishes that when an unbalanced vector force hits an object, the object accelerates. But it doesn't just instantly fly off. The object physically resists this acceleration based entirely on its mass. This diagram compares an empty shopping cart and a loaded one. The loaded cart's greater mass means higher inertia. To force it to accelerate at the same rate as the empty cart, you must apply a significantly larger vector force. Force, mass, and acceleration are permanently locked in this mathematical ratio. If you know how heavy an object is and how hard you push it, you know exactly how fast its speed will change. Up to this point, we've looked at single objects reacting to a push or a pull. But the universe doesn't allow forces to exist in isolation. This brings us to Newton's third law of motion. For every action, there is an equal and opposite reaction. Think of a baseball bat violently striking a pitched ball. The batter applies a massive forward force to send the ball into the outfield. At that exact fraction of a second of impact, the ball hits the bat right back. It delivers the exact same intensity of force in the exact opposite direction, which creates a logical problem. If every single push in the universe is met with a perfectly equal and opposite push, why doesn't everything instantly cancel out to zero? How can anything move at all? Diagram 4 in this illustration shows the answer. Action and reaction forces never cancel out because they apply to entirely different bodies. The bat pushes the ball, and the ball pushes the bat. They act on separate targets. This applies to invisible forces too. Looking at this diagram of gravity pulling an apple from a tree, the Earth exerts a downward force on the fruit. Simultaneously, the apple exerts an exact equal upward pull on the entire planet. We never see the Earth rush upward to meet the apple because of the second law we established earlier. The Earth's mass is so colossal that the tiny acceleration caused by the apple's pull is mathematically insignificant. Independent movement is a physical myth. It is impossible to push, pull, or interact with any piece of the universe without it pushing right back with equal intensity. Once you understand vectors, inertia, and paired interactions, the mundane world around you starts to look incredibly active. A simple book resting quietly on a desk is not actually at rest. It is locked in a high-stakes physical standoff. Gravity constantly drags the book downward. The desk physically compresses and pushes back upward with matching intensity, a continuous counterstrike known as the normal force. This exact balancing act is what holds our world together. The structural stability of the Great Pyramids, like the tension in a suspension bridge, and the orbit of planets around the Sun, all rely on forces meeting, matching, and maintaining equilibrium. Nothing acts alone. Every single object, movement, and resting weight is locked in an unending, perfectly balanced mathematical conversation.